this is my Physics 2211 Lab 3, the mass of a black hole. So the goals for this lab for part 1 was to find a unique mass of a black hole using a computational model that simulates gravity between the star and a black hole. Then for part 2, we were going to find the initial velocity of a spaceship flying near the black hole that goes very close but does not crash into it using a similar computational model from the first part. And our findings were that the mass of the black hole was equal to
1.03 times 10 to the 34th kilograms.
The initial velocity of the spaceship was negative 4.1 e to the 7 for the x component, 2.2 e to the 6 for the y component, and 0 in the z component, and this was all in meters per second. So our key ideas for part 1 were mostly using Newton's second law, but also these equations for the gravitational force. We used the star to collect measurements on the parallel, perpendicular, and net force to measure the mass of the black hole. Then we manipulated equations using Newton's second law, and we were able to use the total net force is equal to the parallel plus the perpendicular forces. And the system we were using for this first part is just the star and the black hole, and everything else is the surroundings. So here's the glow script code for the first part. Here's my email, which is what makes the black hole have a unique mass. These are our given values for this code. This first while loop is what calculates the velocities of the star in the x and y directions. And then using the calculated velocities from the first while loop, we are able to find the final velocity. Then we have the changes in velocity and momentum, and we find the parallel and perpendicular forces. And then using the mass gravity equation, we can find the mass of the black hole. So then here are our glow script results. So I'll run the video. So the parallel line points in the direction of the momentum, and the perpendicular line points towards the center. And then our equations left us with a lot of mass values, and so I calculated the average of the mass. So for the second part of the lab, we are looking at the same key ideas with the equations for Newton's second law of motion and for the gravitational force. We are going to be looking at a spaceship that launches off of a planet that is orbiting the black hole, and the spaceship will approach the black hole but leave before it crashes into it. And so we're going to be focusing on the gravitational equation for this part. So here's the glow script code for the second part. So the first part we see here is the mass from part 1 and the other constants, which is very important that we use the mass from our black hole that we were working with. And then using trial and error, I was able to find initial velocity components for the spaceship that would allow it to approach the black hole without crashing into the planet or the black hole. And then on the right, we were using the F-grav equation as our main part. And so we found the F-grav on the planet from the black hole, then the F-grav on the planet from the ship, and then we found the net force on the planet. And then using the same equations just for the ship, we found the F-grav on the ship by the black hole, and then the F-grav on the ship by the planet, and then the net force on the ship. And then we used the position update formulas for both the ship and the planet. So here are our results. So we can see that the spaceship, which is in magenta, moves towards the black hole, but does not crash into it and turns away from it quickly. And then we can see the planet, which is in cyan, is rotating. And so that was in the video, and then there's just an image of the finished one after 10 minutes. So what does this mean? How do the net force and its parallel and perpendicular components differ? So we have that the F net equals dp dt, and so the difference from part 1 of this lab where we were solving for dp dt, and we concluded that it was actually equal to the net force, which means we are really just deducing the value of the net force. So what if instead of taking a quick look at the black hole and leaving, we wanted to orbit the black hole similarly to the planet? we would need an initial velocity of negative 2.3 e to the 5 in the x direction and 1.1 e to the 7 in the y direction, and it would take approximately 120 minutes. Thank you.